Okay, so we are going to look at a problem relating to the interaction of multiple objects on a single object in dealing with the gravity on that object. So the force of gravity on one object caused by more than one object in its vicinity. So I have 3 billiard balls on a pool table here, and mass 1 is the ball that we're interested in. What is the net force, the net gravitational force acting on mass 1 as a result of mass 2 and mass 3? All right, so we're interested in the net force on mass 1. What is causing that net force? Well, we have a force of mass 3 and we have a force of mass 2. Now, if we conceptualize this first, we know that there is a gravitational force from mass 3 on mass 1 that's attractive towards mass 3. So there's going to be a force caused by mass 3. We're going to call that F3 in the direction of mass 3. We also know that mass 2 is exerting a gravitational force towards it, and that in our case is going to be straight up, and that's going to be the force caused by mass 2. Now, I drew those arrows slightly different lengths. Why was that? Well, the length of the arrow, remember, gives us an indication of the strength of the force, and I'm predicting that the force from mass 3 is a little bigger than the force from mass 2. All 3 masses are the same, so we know that the mass component of that force is similar in both situations. But the distance between mass 1 and mass 2 is slightly bigger than the distance between mass 1 and mass 3. And we know from Newton's law of gravitation that the further away I get, the less the force that's exerted. All right, so how do we calculate the net force acting on mass 1? Well, just like we did net forces in the past, we're going to look at each force individually acting on mass 1, considering its direction, and then putting it together in our vector form. So let's start with force 3. We know that for both of these forces, the force of gravity is going to equal G times mass 1 times mass 2 over the distance between those 2 masses squared. So force 3 is going to be G times M3 times M1 all over the distance, I'm going to call that D3 squared. Now, keep in mind, this M1 and this M2 are my generic. This is that generic equation. I'll just put that in a block and remind us that this is generic. So although this is the force between M1 and M2, I'm not using M1 and M2 in that particular example. All right, so now we just kind of plug in our numbers. We know that G is equal to 6.67 times 10 to the negative 11th. Mass 1 is 0.300. Mass 3 is 0.300. And that's all divided by 0.300 quantity squared. And when I calculate that value, we see that the force of 3 on 1, so by 3 on 1, is equal to 6.67 times 10 to the negative 11 newtons. All right, rounded, of course, to 3 significant digits. Okay, this is pointing to the right. We know that based on our picture. So there's only one component, horizontal. What about force 2? Well, that's going to be G, M1 times M2 over the distance 2 squared. So the distance between those 2 squared. So again, G is 6.67 times 10 to the negative 11. M1 is 0.300. M2 is 0.300 all over 0.400 quantity squared. And when I plug that into my calculator, I've already done that, we end up with 3.75 times 10 to the negative 11 newtons. This is pointing upward. So this is at 90 degrees. This is at 0 degrees for using a coordinate system. So how do I get the net force? Well, this is just like we did net forces when we were doing a force analysis. the net force, the magnitude of that force is going to equal the horizontal component squared plus the vertical component squared. Take the square root. So I have one force of 6.67 times 10 to the negative 11 pointing to the right, one force of 3.175 times 10 to the negative 11 pointing up. I'm going to use Pythagorean's theorem to get the net force acting on that object, and we find the net force acting on that object to be 7.65 times 10 to the negative 11 newtons. So that's the magnitude of my force. And the angle, of course, is the inverse tangent of the vertical component, 3.75 times 10 to the negative 11th, over the horizontal component, 6.67 times 10 to the negative 11th. And we find that equal to, my angle, 29.3 degrees. Now that's the answer that's given out of the calculator. Whenever we do Pythagorean's theorem and get our angle, we want to think about it for a second. Remember, the tangent, the inverse tangent, gives us the first and the fourth quadrant. So we want to think, this is saying first quadrant, does that make sense? And in this case, yes, it does. I have one to the right, one up. The resultant is going to indeed be in that first quadrant. So 29.3, with respect to the horizontal axis, of course, seems like an appropriate quadrant for that angle to show up in. All right, so we can use Newton's law of gravitation to again look at the net force, the net gravitational force on a single object by just looking at each force individually and then using our vector algebra to put it together. Good job.